This is a weekly summary of interesting news that is relevant for my lectures at the Eastern Switzerland University of Applied Sciences. My name is Thomas Bocek, and today we will discuss 4 topics. The first topic, it's the following here, and in my videos I talk about self-hosting, mostly the positive aspects, and this article shows what can go wrong if you self-host without proper research on the project you're running. Gogs is a popular self-hosted Git service written in Go. It's a lightweight alternative to GitLab or GitHub that many developers use for their infrastructure. And about 1,400 Gogs servers are publicly exposed on the internet right now. And security researchers here, they discovered in July that a zero-day vulnerability exists while investigating malware on a customer system, and the vulnerability is a bypass of an earlier security fix. And the original problem allowed attackers to write files outside the Git repository through path traversal, and the developers fixed this by validating the path, but they didn't account for symbolic links. And here's how the attack works. An attacker creates a repository and commits a symbolic link that points to a sensitive file outside the repository. And when they use the API to write data to that symlink, the system follows the link and overwrites the target file. And by overwriting the git config file, they can execute arbitrary commands on the server. The attack started July 2025 and is still ongoing, and over 700 instances have been compromised, which is more than 50% of all exposed Gogs server. The attackers use automated tools that create repositories with random 8-character names, and they deployed malware based on a framework called Supershell, which establishes remote control over the compromised systems through a reverse SSH connection. And the vulnerability affects all Gogs version up to 13.3, the recent one. And as of today, right now, there is no patch available. The developers were notified in July, but haven't released a fix yet. The default configuration of Gogs enables open registration, which means anyone can create an account and exploit this vulnerability. Also on their GitHub page, they don't use Gogs for whatever reason. There seems to be no activity on this issue, and here is a guy asking about the status. That means if you plan to self-host, make sure the project is healthy and not like Gogs. The next article, it's the following here. This article challenges the assumption that you need networked databases like Postgres for web applications. So when you compare the benchmarks here, Postgres with no network handles around 17,000 transactions, while SQLite handles around 20,000 transactions per second, so slightly more. However, if we add network latency, the performance collapses. Postgres here drops to around 5,000 transactions per second. And this shows how latency has an impact on performance. And the problem comes from interactive transactions where application code runs between the queries. Each query needs a network round trip while holding database log, and with higher contention, these logs block other transactions and you cannot scale out of this by adding hardware. And there's also a nice catchphrase here. What's terrifying about this is no amount of additional CPU server memory is going to save us, so latency also matters. And SQLite runs embedded in the application. There is no latency, no network, And with batching and nested transactions, it can even reach more than 100,000 transactions per second, including concurrent reads. And for distributed systems, this shows that distribution has a fundamental cost, and network latency is not just a performance issue, it changes what throughput is possible. And the article also shows the trade-off between single writer and multi-writer system. SQLite is a single writer, which sounds like a limitation, but it enables trivial batching because all writes go through one point. Multi-writer systems like Postgres need coordination and retry logic for serializable transaction, especially under contention. The next article is about stealth addresses. It's the following article here, and it explains how Monero achieves transaction privacy on a public blockchain. In most blockchains like Bitcoin, all transactions are public. If you know someone's wallet address, you can see their entire transaction history. And Monero solves this with stealth addresses, which are one-time addresses that cannot be linked back to the recipient. And the article explains how this works. So Alice wants to receive payments, but doesn't want anyone to know her wallet received them. So she publishes two public keys, a view key and a spend key. And when Bob wants to pay Alice, his wallet generates a random number and uses elliptic curve math to create a temporary one-time address. And this address appears on the chain, but it looks completely different from the public address of Alice. And the technical process using is elliptic curve Diffie-Hellman key exchange. Bob creates a shared secret with Alice without directly communicating with her. He does this by combining his random number with Alice's public view key. Alice can compute the same shared secret by combining her private key with information Bob puts on the chain, and both arrive at the same secret number. And with this shared secret, Bob constructs a payment address that only Alice can recognize and spend from. Alice scans the chain for payments that match the pattern created by her keys and the shared secret. And when she finds one, she can calculate the private key needed to spend those funds. Nobody else can determine that this payment went to Alice because they don't know the shared secret. And the system also uses ring signatures, which makes it impossible to determine who sent a payment. When you combine stealth addresses with ring signatures, the blockchain shows transactions happening, but you cannot reveal who sent or received them. And now for the most important news, it's about the challenge task. This semester's challenge task in the blockchain lecture is about design and implementation of a gasless application using account abstraction. And the goal is to demonstrate how users can interact with blockchain applications without owning or paying gas fees. And the app needs a simple web-based front end that runs on a public blockchain. The backend runs on a public blockchains. If you use EVM chains, you can use ERC-4337, or you could use chains with native account abstractions. And in order to pass this lecture, you need to have a working prototype with at least 2 users, and the users do not have to pay gas. Of course, the status needs to be shown in the front end, and if you use other libraries, you need to take the latest stable releases. So, and for the winner, and now I need some drum rolls. And the winner is Group 7, Jovin and Lenny. The group build vote 3, it's a gasless e-voting prototype with a potential e-ID use case. In their tech stack, they used React frontend with Vite, Alchemy for account abstraction, Hardhat for smart contract deployment, and they used the Ethereum Sepolia testnet. They implemented 2 smart contracts, voter pass for voter eligibility and the other one for the voting logic. The account abstraction flow routes transactions through a bundler entry point and smart contract wallet with a paymaster sponsoring all gas fees. And the prototype demonstrates the complete gasless experience. Users connect with MetaMask, voting proposals, and the platform covers the transaction costs. Well done, and it was a difficult choice, and there were other very good cases, but this stood out due to the interesting use case. Another very good use case was the flat fee stack group, but since I proposed this topic to the group and I'm heavily biased to this topic, I had to exclude this. So congratulations again to Jovin and Lenny, and this channel goes into the Christmas break and resumes operation in February.